Okay, so I'm doing this immediately after we just talked in class. I just wanted to do a complete walkthrough for anyone who wanted to watch this later, sometime before our quiz on Friday. So for this, I want to talk through problem one to start. So this is our double slit diffraction problem. We have something like this, with two slits separated by a distance d. And then over on some far distant screen, some distance L away from our source, or from our slits, I should say, we have some interference pattern forming. And these two rays of light are taking two different path lengths to get to some location. There's the center, then this would be, say, like Y1 for the first location where they are interfering constructively away from the central maximum. So the difference in path length is then d sine theta, where theta is this angle here, which is the same as this angle here, assuming that y is much, much smaller than L, then we can make that assumption, the small angle assumption, where sine theta is approximately tangent theta is approximately theta when we measure theta in radians. And you can test this yourself that this holds up pretty well for any angle smaller than about 15 degrees. And you may want to try that on your calculator just to prove to yourself that this is accurate. You can just plug in sine theta and tangent theta of theta being like 10 degrees or 5 degrees and see that the answers that you get should be very close to each other. Okay, so now we know that this is the path length difference, that the path from this lower slit takes a little bit of a longer path to get to that distant interference where they interfere constructively. And so that d sine theta, being that path length difference, must equal some integer number of wavelengths of our light. And in this case, if we're talking about the very first time they interfere constructively away from that central maximum, n would be 1, and so d sine theta would equal exactly 1 wavelength. So let's see. We could then solve this formula and say, since we're trying to find the wavelength of our light, this would be d sine theta over n. And we were given, in this case, a couple different pieces of information, including the slit width d, which we need. But also sometimes we were given the angle theta, or sometimes we were given the distance y from the central maximum. So if we were given theta, we could use our small angle approximation to tell us that I can replace sine theta here with just theta. And this would then be d theta over n. And that's all I would need. If I'm given the angle, I don't actually even need to know how far away those slits or those diffraction pattern is from the slits, because that angle is the same no matter how far away the diffraction pattern is. But further away that the diffraction pattern is, y is going to get bigger because theta is going to be the same. So it's the amount, the physical distance that that angle subtends will increase as L increases, as the screen gets further and further away from our slits. So the other piece that we can do here, if we're given y and L, we can say sine theta is approximately tangent theta. And then lambda equals d tangent theta over n. And tangent theta, if I draw this big triangle, is opposite over adjacent, so y over L. So then I could say that lambda equals d y over L times n. And then I would just plug in all these values, and in this case, I would get something like A, B, C, D, E. The wavelengths would be something like 650 nanometers. This would be about 1350 nanometers. C, 503 nanometers. Then we'd get about 1400 nanometers. And lastly, 700 nanometers. And be careful as you plug these numbers in to double check all of this, that you're plugging in the right value of n, because sometimes here I gave the y1, the distance to the first peak, but sometimes I gave y2, the distance to the second peak, second time that it's maximized. And then in that case, n in those formulas, when we're measuring to y2, n would be 2. And so we'd have to account for that. Also, there was one where we had theta 2, and so we'd use this version of the equation here, except we'd plug in n equals 2 for that one. So that's the first problem. Take a look at the solution as well, and hopefully this helped walking through double slit diffraction. So then I want to then talk about the second problem, which is more related to single slit diffraction. Here, we have just one opening in kind of our seawall protecting our harbor. And this opening, which I'll call A, is about, 50 meters wide. And we're going to see that waves coming in here are going to end up diffracting outwards and hitting our distant shore, some, in this case, distance away. But we want to know, relative to this central line that we could draw from our opening to the distant shore, what angle, theta, should we build our pier to protect our boats from all these waves? So there's going to be some minimum that these waves are going to deconstructively interfere at some angle, where they're going to add together peak to trough and they're going to cancel out. So in this case, what we're going to do, if I zoom in on that opening, again, as a width of A, I'm going to say, what if I take a wave originating from here, going off into the distance, and a wave half of A away from that, going off into the distance, and have them say, we're going to have those deconstructively interfere far away. Well, if I make this little triangle, call that angle theta, which should be the same as this angle that we measured over here, theta. Well, this is A over 2. And then this is A over 2 sine theta. So that's the path length difference between these two waves as they travel to that distant point. So A over 2 sine theta, if I want deconstructive interference, or destructive interference, I should say, they should differ by half of a wavelength. So then we would get peak adding to trough and they would cancel out. So here I can say A over 2 sine theta is lambda over 2, and I can cancel these 2's to get A sine theta is lambda, and sine theta is lambda over A. And finally, theta is the sine inverse of lambda over A, and then I can plug in my numbers, and I would get theta is about 23.6 degrees. So we would know then where we should build our pier, 23.6 degrees away from that central line. So that's single slit diffraction. We could do the same exact math with light rather than water waves, but this makes a kind of a more kind of common in real life example of how this could be applied. So if we know the wavelength of the waves we expect to hit our harbor, we would know where to build our pier to minimize the effect of those waves on the boats. Okay, lastly, I want to go through again that last problem on thin film interference. I know this one was challenging. So if we have a thin film of oil having 1.45 index of refraction with air above and water below, then we could figure out what wavelengths of light are going to interfere given some known thickness. Or we could go the inverse, which is what this problem is, and say, I know what wavelengths of light are interfering constructively. What are the possible thicknesses of this oil that would give me that interference? So to figure this out, we need to know when are we going to get constructive interference up at this upper surface from white light coming in perpendicular. Some of that light is going to reflect off, and that is going to have a phase shift because we're going from a low index of refraction to a high index of refraction. And so we would get a phase shift there equal to half of one wavelength. So in order for us to have constructive interference from this light that gets transmitted and reflects back, whatever happens to this light beyond this point when it gets transmitted from the first surface, it better equal 1/2 of a wavelength of phase change in order to constructively interfere with this light here that I'm labeling now in orange. Because now if I draw this one again in a different color to differentiate it, when this orange and this blue ray come together again, if they want to interfere constructively, they need to meet peak to peak. So let's take a look at this lower surface to figure out whether or not there's a phase change there. In this case, we're going from a high index of refraction to a lower index of refraction. So there's no phase change. We know there's this phase inversion, this phase change of half of a wavelength, only when we're moving from a medium in which the wave moves fast into a medium in which it moves slowly. So here, inside the oil, the wave moves slower, and in water, it would move faster. So there's no phase inversion at this interface. But we do have a difference in path length equal to twice the thickness of this oil, which I'll call T. Twice because we go from the top surface down a distance T, and then again from the bottom surface back up, again a distance T, so we get 2T distance in the path length. So we know that that's got to equal half of a wavelength within the oil in order for it to interfere constructively up here. Now, I said in the oil because lambda oil is not equal to lambda in air. It's actually somewhat reduced because of the index of refraction of the oil itself. So we can say that this thickness, this twice the thickness, the path length difference should be equal to 1/2 lambda oil, but it could also be, so if I say we want this to meet up at a peak, and right now this is coming in at a trough, it could be half a wavelength, but it could also be 1/2 plus another half plus another half, 3/2 lambda oil. So this is 1/2 lambda oil. And we can keep adding one full wavelength to this. So we could go here and then another 1/2, another 1/2. We could have 5 halves lambda oil so that we get another peak adding to this peak. So here, I'm going to actually add in an M, saying M being an odd integer, 1, 3, 5, 7, ... And then we would have everything we would need. So here, I'm going to place this, and here I'm going to go 1/2 lambda oil with lambda over N, where N is N oil is 1.45, and I'll solve for T. T equals now 1/4 lambda over N times M. Now we could do what I did in class and say, let's just start listing off all the possible values of the thickness given different values of N for each of our wavelengths. So we could do that and say for lambda equals 700 nanometers is one of our 2 wavelengths that interferes constructively. And we could list off values of M and see we would get 1.2 times 10 to the minus 7 for M equals 1. Then we get 3, 5. We get here 3.6 times 10 to the minus 7 and 6.0 times 10 to the minus 7. All of these are in meters. And then we could do the same thing again, but for the other wavelength that we had. So 500 nanometers light. And say for M equals 1, we'd get 8.6 times 10 to the minus 8 meters. We'd get 2.6 times 10 to the minus 7 meters, 4.3 times 10 to the minus 7 meters, and 6.0 times 10 to the minus 7 meters. And here we could say, finally, we recognize that there's only one true thickness to this oil. So the one that agrees between these two has to be the true thickness. So in the answer here has to be T equals 600 nanometers, or 6 times 10 to the minus 7 meters. Now, I want to also show you another little trick that makes this even a little bit easier. We don't have to list off all possibilities. So once we get this formula, that T equals 1/4 lambda over N times M, we could say, well, there's only one true thickness. So this is always going to be a constant. And N, this is N oil. This is always also going to be constant. So the two things that differ between the red light that is interfering constructively and this kind of greenish light that is interfering constructively at the surface is the only difference is how many of those wavelengths are we traveling? Are we traveling 1/2 of a wavelength, 3 halves, 5 halves, 7 halves, and so on of this wavelength? So M is going to change and lambda will change, but everything else is going to be the same. So what we can do is say, let's set them equal because both of them are going to be equal to T. 1/4 lambda 1 over N oil times M1 is 1/4 lambda 2 over N oil, M2. Because so this lambda 1, let's say that's the 700 nanometers, has some M associated with it. Lambda 2 is the 500 nanometers, also has some M associated with it, but they both have these 1/4 and the N oil is the same. So here we can multiply both sides by 4 N oil and cancel those terms because it shows up on both sides of the equation. So lambda 1 M1 equals lambda 2 M2. Now, this doesn't quite get us there quite yet, but we do know lambda 1 and lambda 2. So I'm going to put the lambdas on one side of the equation and the m's on the other. Let's say lambda 1 over lambda 2. So I'm just dividing lambda 2 to this side. I'll then have to divide m1 to the other side as well to get m2 divided by m1. And now I can plug these numbers in. This is 700 over 500. Well, I can simplify this ratio and divide top and bottom both by 100. So then that this has to equal 7/5 as well. Now we know these m's have to be odd integers. Well, look at this ratio. This on top is an odd integer, and on bottom is an odd integer. So one possible solution to this is m2 equals 7, m1 equals 5. Well, that's a possible solution. So let's see what that leads us to in terms of thickness. T is 1/4. Let's pick lambda 1 is 700 nanometers divided by 1.45 for N oil times the M1 is 5. And that would give us, we'll plug in some numbers. We'd end up seeing that this is 6.0 times 10 to the minus 7 meters, or 600 nanometers. Now, this is a little bit of a trick that I wouldn't necessarily expect you to come up with, but something that once you do enough of these kind of problems, you'll start seeing that this is something that can be useful to do. That when you have, in this case, we know the thickness is the same and oil is the same. The only thing that differs between the light is the wavelength and how many wavelengths it travels. What is the value of m as it goes from here to there and back to constructively interfere at the top surface. But we could see that we could plug in the other of these. We'd say 1/4 now 500 nanometers over 1.45 times now m is 7. And of course, we could see 500 times 7 is going to be the same as 700 times 5. And so we will get the same answer of, again, 600 nanometers. So that's one way of trying to solve this. But generally, in terms of strategy on how to solve these kind of problems, think about where do these phase inversions happen? Which surface is going to be inverted or not? Think about the path length difference that the light that's transmitted and then reflected from a different surface is taking so that it comes back to interfere constructively or deconstructively at that surface. And then put together an equation relating those things, the condition for constructive interference that we had here, or maybe you're looking for destructive interference and then you have a different condition. Or maybe you have different materials leading to different locations where you get this kind of inversion or not. All of that information will lead you to an equation relating the thickness to the wavelength of the light in whatever medium it's traveling, that extra path length. So in this case, it was traveling in oil, so we needed to think about the wavelength in the oil. And then you come up with some estimate of the thickness. And maybe you have to think about what are all the different possibilities for that thickness. In this case, we needed to list them out and figure out which one agreed with both of our observations. Because there were multiple possibilities for the thickness, but we knew there's only one true value, and we had to figure out which one agreed with both observations of red and green light. Okay, so I hope that this helps. Try doing a few more practice problems of thin films and interference patterns with slits either single slit or double slit diffraction. Ask me questions, and I will see you guys on Friday. Bye.